underground air circulation modeling in the St Marcel d'Ardèche cave that we made with two other students of the IMT Minales engineering school. So the St Marcel d'Ardèche cave is located in St Marcel d'Ardèche. It was discovered in 1836 by a hunter whose injured rabbit was hiding into a small hole into the natural entrance of the cave. Today we know more than 60 kilometers of galleries in the cave. Yes, there is a height difference in the cave of 238 meters, right? There is minus 101 meters and plus 137 meters with the 0 meters, which is the natural entrance. Here is the situation of the cave. We have here the natural entrance, and approximately here there is the touristic entrance. Today, tourists don't have access to this part of the cave, but this is this part of the cave that we had to modelize during this work. I'm going to talk about a little bit about the entrance of the cave and how it was how it is closed. From the discovering of the cave, when the cave was discovered, the natural entrance was obstructed with a concrete wall and a very big door, like you can see on this picture. This door was damaged during a flooding in 2002 and was replaced by a grid. I didn't precise that the concrete wall didn't allow bats to enter the cave. And when they replaced the door by a grid, the bats could come back in the cave to hibernate. In 2017, the concrete wall was destroyed, was totally destroyed and replaced by wooden panels. There are several wooden panels in order to be able to have different opening surfaces on the natural entrance. So the big question that we had during this work was what is the best opening surface of the cave in order to optimize the living conditions for the bats to hibernate in the cave. And we kept in mind during this work that the best living conditions for chiropterans are a ventilated cave without too high velocities of air and a stable temperature in the cave. We did the modeling with the software ANSYS Fluent based on measurements of the cave. ANSYS Fluent uses the finite elements method applied to a mesh. We used several hypotheses that are here. The materials that we used are for the fluid air, which was already registered in the software. And we registered two new materials for the walls, limestone, and for the panels, wood. The climatic conditions, the modeling is during the hibernation period of the bats, so it's during the cold period from mid-September to mid-April. And during this cold period, the cave aspires, which means that the climatic conditions of the inside of the cave depends on the climatic conditions of the outside of the cave. Knowing that, the hypothesis of temperature that we took is for the outside 7.6 degrees Celsius, It is the average temperature that was measured during the cold period just at the entrance of the cave. And for the inside, we used the chopping method to calculate the 10.4 degrees Celsius that we took at 61 meters of the entrance of the cave. The airflow was measured just at the entrance of the cave, and it was 2.9 cubic meters per second. The meshes, it's an important parameter to take into account, the meshes, because if you take too small, if the meshes are too big, you can't, there will be some approximations due to next to the walls, some oscillations due to some limits of the software. But the software can't have too many meshes, so we were limited by that. So we took meshes of 40 centimeters high. We ran the model with several opening surfaces, and we calculated the Reynolds number for all these opening surfaces. It was always over 2,000, so the regime was always turbulent. This is the geometry of the cave that we used. It's a very simplified geometry, very simplified model with very simple geometrical shapes. The cave is modelized only in the first 100 meters. The entrance is here, and we varied the opening surface here. We ran the model with 2,500 iterations. So here are the results that we obtained. So for the different opening surfaces that I wrote here, here are the temperature distributions in the cave. So we can see here each time where is the opening. So for all the opening surfaces, we had a temperature that was smaller on the ground than on the ceiling, which can be explained because the cold air is wetter than the warmer air, so stays on the ground. And for the opening surfaces over 5.7 square meters, the temperature is homogeneous on the sections more quickly than for the small opening areas. And when there is less variation in the end of the part of the cave that we modelized for a smaller opening. So that shows that the less the opening, the less the cave is opened, the less the bottom of the cave is the climatic conditions of the bottom of the cave are impacted by the climatic conditions of the outside of the cave. Yes. Now we have here the air speeds for all the opening surfaces. When there are the small opening surfaces, preserve the cave from too high velocities. So here we can see that there are some areas where the velocity is not very high, near from the entrance, and for bigger opening surfaces, it's not the case. And when the opening is smaller, the air enters the cave with higher velocity. But with a bigger opening surface, there is a better repartition of the incoming air in the volume of the cave. Here are the same. It's not the temperature. There are the speeds, but there are the speeds on the section of the cave. We can see here that the velocity of the air is way higher in the alignment of the opening, and that there are spaces where the velocity of the air is very small for small opening, which is not the case with big openings. So to conclude, our recommendations for the opening of the cave, according to knowing the best living conditions for chiropterans, were to have an opening of 3.8 square meters per second. No, square meters, sorry. Because the cave was ventilated. There is air that comes from with some velocity, but not too high velocity, and there is a part of the cave which is preserved from high air velocities, and the temperature is stable on the section more nearer from the entrance than with bigger openings. Thank you.